Let's take a quick look at statistical process control, or what we refer to as the voice of the process in quality engineering, using a basis of statistical analysis to understand whether our processes are in control or not. Basically, if we have large amounts of data in our process that we're looking at, what we're hoping to do is to identify whether or not our processes are in statistical control or not. Are they predictable in the sense that in the future they'll behave like in the past? So it's not that we expect them to occur without variation, but it's a big difference in how that variation occurs, and we want to be able to measure that statistically. So the S in SPC, or statistical process control, means we're analyzing something statistically, looking at variation and measurement. The process is a group of related activities, so we might be looking at the way a process works, or the way a product works, or a product design. And what we're ultimately doing is using a feedback loop to bring statistics back into controlling a process to see if it varies. So does the process behave the same way over time? Whatever variations are in it, are they statistically predictable? And can we use the data to identify when some exceptional case happens that we would want to address as engineers? So basically, as we collect data about a process, what we want to be able to do is collect enough data that data can be expected to behave in a normal way statistically. So we're typically looking at a sample of data that has to include at least 25 or so data points, sometimes as much as 30. So if we've only measured our process a couple of times, the sample size would be so small we wouldn't be able to determine whether it was in control or not, and certainly not why it was out of control as we go. So we're looking to create a set of charts that will depict the process over time such that we can spot variations in the process that would be considered exceptional. We're looking basically for two different kinds of variation, what's known as common cause variation, the everyday normal differences in what's going on in a process that would cause it to have variable output each time it executes or each time we do it, but that would be considered perfectly normal. When you drive to the store or you drive to school, you never take exactly the same amount of time to get there. So you've got traffic lights and you've got traffic and you've got various kinds of conditions that would be considered common cause. They're everyday ordinary occurrences. But you might have things that stand out, what are referred to as special causes. You might have a flat tire, you might run out of gas, there might be an accident on the highway that causes traffic to divert. Those kinds of things aren't expected to happen every time a process happens, and we could devote some energy to trying to make sure that they don't happen. So we refer to those as special causes. We want to be able to differentiate the two. Special causes, by definition, are things that we can economically attack as engineers and try to alleviate. Common causes are harder to reduce. We might be able to improve the performance of our system if we improve common causes, but typically we've got to change the system in order to do that, and that can be very difficult to do. So the common causes are always present. Their individual impact tends to be small, but collectively they can be quite large. So it might take you a long time to drive to work in the morning with a lot of different variables causing that. Every one of those variables is different every day, but cumulatively they cause you to take a certain amount of time to get to work. Special causes happen only occasionally. They're typically something outside the process you're looking at, and the impact of a single cause can throw the whole process out of whack. Things like weather are common causes as things go through. But a major storm or a flood coming through would be considered a special cause in your travels. Traffic patterns, traffic lights, things of that nature could be both cars, traffic coming through, exceptional cars or accidents coming through. You need to be able to look at a process and differentiate variation that you would expect to see every day from variation that would be very, very rare and that you might want to look to prevent or change in the future. Walter Shewhart was the father of statistical process control, and he defined statistical control for us back in the 1920s. Basically, the process is under statistical control if we're able, based on our past experience, to predict within limits how it will behave in the future. So if a process is subject to only common cause, we can very highly reliably predict what it will do in the future. To do that, we basically want to build a series of control charts. We want to look at past experience and chart that data, establish what the controls are in step 2, how wide do we expect the process to be, and then use it to predict the future going forward. So we start by plotting the data in time order. So we take a set of data out of our process, maybe how long it takes us to get to work every day, or how many defectives we produced yesterday, or whatever we're choosing to measure. We plot that data over time. We then take the average of that data, of the point plots, and determine what the average behavior of the system is. What is its mean value over time? From there, we want to establish how much variation can we handle before we would realize that the process is not really under statistical control. And for that, we're going to use the empirical rule in statistics. Basically, we're going to look at plus and minus 3 sigma around our average, that most of the data under the empirical rule will fall within 3 standard deviations of the mean over time. If we get a data point outside of those limits, we'll know that that must be an assignable cause. It is so extreme that statistically we would not have predicted it would happen. Things we look for in special causes: we look for data that might be shifting toward the high or the low. We look for trends. Trends in the data are considered special causes, and cycles that occur in the data. So not all of the statistical outliers will be those that fall outside the limits, although that's the ones we usually talk about. But really, any data that establishes non-random behavior and variation would be considered something we'd want to look at in terms of special cause. There's a set of rules that come out. You can see them in most statistical tools for the ways you tend to look at it. We're basically expecting the control chart to be a normal distribution lying on its side. So we expect to see points back and forth among the 3 sigma distribution, with most of the points toward the center, but definitely some points easing toward the side, the same way you would expect to see under the normal curve. We know those as the Western electric rules. So basically, if this data points fall within that plus and minus 3 sigma in our control charts, we'll know we're looking at pretty much common cause variation if in fact the data is bouncing around. If we see those trends or cycles, we'll know we're not. And if we see data outside those 3 sigma limits, we'll know we're also seeing a process that is not in control. So Shewhart basically invented this process and had its plot over time, really wanting to use the 3 sigma limits, which we have to estimate. We don't know the sigma for our population, but we do know the standard deviation for our sample. And we can estimate 3 sigma for the population over time, and the empirical rule shows us that most of our data will fall within the control limits. So the empirical rule basically shows us the normal curve, where most of the data is within 3 standard deviations, half the data to each side of the mean, about 68% within 1 standard deviation, 95% within 2 standard deviations, and almost 100% within 3 standard deviations. So those small percentages of data, 0.135%, that fills in that remaining, those are going to be the data that would be the outliers. So we know just from basic empirical rule in the normal curve that most of our data should fall within the control limits, and if our process is under control, our data points will in fact fall within that range. We use 3 sigma limits largely because if we used tighter 2 sigma limits, we get too many false alarms. We expect to see a bunch of data near 3 sigma, and if we used a 2 sigma limit, the chart wouldn't work. We'd constantly be chasing down variations that are actually naturally occurring. Likewise, if we used 4 sigma limits, we'd miss all but except the most drastic changes, and we want to be able to spot something. The whole point of doing this technique is to spot things that are going on in the process. So these charts allow us to measure and stabilize around a good desirable amount of variation that was in 3 sigma. That's the whole purpose of the control charts as we go through. So of the types that are there, the variable control chart, typically the X bar and R chart. The X bar is mean and the R is the range. The X bar R chart allows us to measure a process that's using a continuous variable. So if you're dealing with continuous variables like the length of a rod or things of that nature, the amount of time that's passed, things you can actually measure to significant decimal places, you're typically looking at a variable control chart. Like I said, things you can measure. If you're looking at attribute control charts, the P and the NP, the C and the U, those are things that are based on proportions and densities for discrete distributions. So things like the number of defects in your process would be measured using a C chart. The number of defectives coming out of your process would be measured in a P chart. Basically, if you count it rather than measure it, you'll use an attribute control chart. Some of them being based on a binomial distribution and some of them being based on a Poisson distribution. The variable control charts are all based on the normal distribution. So our variable control charts basically look at continuous data. It's the one we'll use most of the time for validating a process. How late is it? How much did it cost? Things of that nature. How long does it work? Anything you can measure in your process. As soon as you've got 30 data points to establish the limits, you can create your control charts. Okay. Of the types, you've got the individual and moving range chart, which you can do with very little data. If you've got rarely occurring events and it's hard to get a lot of data, you can actually do an individual chart. If you've got more data, which is more the norm, you can use an X bar and R chart. Of the charts I've drawn in my career, 90% or more have been X bar and R charts. The attribute control charts allow you to look at the pass-fail, yes-no kinds of decisions we see in the binomial distribution or in the density functions like the Poisson distribution related to defects in our process. So we can measure defects and defectives, the most common, but anything we can just have a binomial measure, a binary state can be measured as though it's a defective yes and no, as well as the density of defects or occurrences in there. So project is over budget, we can use C and U charts to measure how over budget it is in terms of dollars. Anything we're measuring, the density or the amount of something that's out of range, we would use that kind of chart. So like I said, there are a family of control charts here. There are actually a dozen or more different kinds of control charts, but the vast majority of them will be the X bar R chart to measure a basic process, and then the P chart or the C chart to track defectives and defects. This is a basic control chart flow to help you decide which chart you're going to be using of all the different charts, the size of your sample size, as well as the type of data you're recording are basically the criteria for knowing which kind of chart you would be drawing. Periodically, you'll be changing your processes. Often the reason you measure a process is so that you can spot a change in it. Not all change is undesired. If you're doing a process improvement effort, the whole point of what you're doing is you're trying to drive the process out of control for where it was to show that you've improved it. And once you show you have, you would end up recalculating the control limits to represent the new process going forward. If you're doing Six Sigma, you're using control charts in the control phase of your life cycle, and a separate discussion on Six Sigma could lay out how all of that happens. Again, you're looking at sample size and types of data in selecting the right chart. On this example, if you've got variable data and a sample size of only one, you'll be using the individual and moving range chart. So the types of charts you'll use will vary based on the type of data you have and the size of your sample. So finally, SPC, or statistical process control, is our tool for measuring the voice of the process, for figuring out if it's stable and reliable. Can we accurately use statistics to predict future behavior of a process? And we can if we can show through our control charts that the process, the way it's behaving, is in fact under statistical control. That doesn't mean it has no variation. It might have an enormous amount of variation, but the amount of variation remains fairly constant and the process stays within its limits.